Hello everyone. In this video, we're going to see about the oral messages, the assumption related to it, the oral message algorithm, and we're going to end it up with some examples. So let's just start with the first assumption that says every message sent is delivered correctly. No message loss. So what it means? If a process sends a message, the message will arrive exactly as being said, as being sent to the destination. No corruption, no dropped packet. So if you receive any inconsistency, you have to assume that that inconsistency came from a line, came from a malicious node and not from the network, right? So we assume messages don't vanish. We assume messages don't get scrambled. If someone says something, it arrives intact. Any inconsistency, if it is there, it has come from the line node, it has come from the malicious node and not from the network. Then let's come to the next assumption that says receiver knows who sent message and because it is completely connected network with reliable links. When you receive a message, you know exactly which process sent that message. There's no spoofing. There's no spoofing of the sender IDs because the network is fully connected, and you can and you can link and reveal certain sender identities. So the assumption is that you have to assume every message that you're receiving as a destination, it is going to come to you with a clear from tag. From means source tag. Recipients know who claimed what, so we can just keep track of the conflicting reports from the reports coming from the different nodes in your network. Then coming to the next assumption that says absence of message can be detected. So, if you were expecting a message in a particular round, in a particular windowed frame, and it doesn't arrive, you can tell it's missing. You don't have to confuse silence with a delayed delivery. You don't have to stay in the loop waiting that, okay, I'm going to receive the message. I'm going to wait until the message comes. No. If you didn't receive a message from in that window, you have to assume that the node did not send a message. And if somebody did not send a message, you're going to assume retreat for that case. We don't have to get inconsistency. It's not like that. If the commander, let's say just the commander chose to not say anything in his windowed frame, we're not going to assume that the commander meant take any decision that you would like to take. No. If the commander did not give any of did not speak or choose to stay silent during a window time frame, all the lieutenant nodes, all the nodes in the network, they have to consider it as a retreat situation. Now, why do we have to consider it as a retreat? Because retreat or because being defensive is a much safer place to be in, right? So yeah, if someone should have spoken in this round, but they stayed silent, they chose silence, we notice missing messages, and that is observable. Synchronous system only. So the system proceeds in rounds with the known upper bounds. We wait until this time to receive a message. And if we don't receive a message in that frame, we consider it that the node chose to stay silent. And now that node meant retreat, right? So there are global gongs, there are global timeouts, after which everyone can safely assume that they have heard everything for the round. And if they did not hear anything from a particular node, they consider that to be a retreat. Why does it matter? Because synchrony is crucial for the all-to-all message exchange arguments and for detecting your missing messages, right? So we assume, the assumption here in this part is that we assume a clocked system. Messages arrive within the known time window, so missing messages and round boundaries are very meaningful. You need to know the upper hand limit. Now let's come to the oral message algorithm. Oral message 0. That is how your oral message algorithm starts. Commander sends his value to every lieutenant. Simplest possible scenario, the shortest possible case. That is, the commander just broadcasts his order, may it be attack, may it be retreat, on a one-on-one basis in a pair-to-pair network order to all the lieutenant nodes, to all the nodes that are hearing in the network. No extra forwarding or relaying happens. It is just between you and the commander, between the lieutenant node and the commander, right? So the commander directly tells everyone his order. That's it. No message passing between the lieutenants. With the next line that goes, each lieutenant uses the value received from the commander or uses the value retreat if he receives no value. That is what I was telling to you in the previous slide, right? If a lieutenant gets a clear order, say attack or say retreat, he will follow that order. The system assumes reliable delivery. So if the commander is loyal, all the lieutenant nodes are going to be on the same page, given the lieutenant nodes are also loyal, or at least even if the nodes are not honest, they're going to receive the same message. Whatever they tell you next is something different, right? But they're going to get a single message from the commander, right? If the commander is honest. So if a lieutenant hears an order, he follows it exactly as it was given or uses the value retreat if he receives no value. Again, the same thing I like to repeat. Why are we why are we going with retreat? Because it's safer to do nothing than to attack with incomplete coordination. Because we studied in the Byzantine rules, right? If it is an incomplete coordination, we're going to have catastrophic failures, right? So this way we just assume that the missing orders, they're not causing any random, any split behavior, any behavior that just says you that go as per your wish. No, if you don't receive anything, just take this to be a retreat. So your oral message 0 only works correctly if your commander is loyal. Because if your commander is not loyal, every lieutenant node is going to hear different order from your commander. Some may hear attack, some may hear retreat, and some may not just hear anything. So if your commander is corrupt, he can send different values to different lieutenants, causing disagreement. That's why your oral message 0 is the foundation, but not sufficient when faults exist. So let's just go ahead and let's just see oral message M, where M is greater than 0, because M equal to 0, we've already seen that. So what happens here? Commander sends his value to every lieutenant. This is same as OM0. The process starts with the commander broadcasting, may it be attack, may it be retreat. This is the initial input everyone works with, right? So for each I, let VI be the value Lieutenant I receives from commander, or retreat if there's no value. So, each lieutenant, what it does, it records what they personally got from the commander. If a message is missing, they just plug in retreat as the safe default, right? So so now what they have to do, they have to act as commander individually for OMM-1 and send VI to N-2 other lieutenants. Why N-2 other lieutenants? Because you're not going to send anything to the commander, you're not going to send anything to yourself. That makes the N nodes go from that makes the N nodes go to N-2 other lieutenants. Now comes the key step, right? Each lieutenant, it just pretends to be a commander for their received value. They forward the commander's order to all other lieutenants, except the commander and except themselves. But this forwarding is not just one step. They actually run OMM-1 with that value, meaning they repeat. It's just a recursive step. They repeat until they go one step smaller, 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 smaller. Make sense? It's like each lieutenant is going to act as a mini commander. They forward the order they got to everyone else, running a smaller version of the same protocol. Then next line that goes by, for each I and each j, where j is not equal to I, let vj be the value Li, Lieutenant I, received from Lieutenant J in the above step, or retreat if missing. After forwarding, Lieutenant I is going to collect the reports from all the other Lieutenants J. Each of these reports is what J claims that the commander said. Now, J could be honest, J could be not honest, right? Again, if something is missing, it's treated as retreat, right? Now, every lieutenant collects what the others say they got from the commander, filling in retreat if something is missing. And then comes the next step that says Lieutenant I computes majority. Now, every lieutenant with all the values that it has received from all its comrade nodes acting as commander in the steps, you have to calculate the majority. And if the majority says attack, it is attack. If the majority says retreat, it is retreat. Right? So this is going to ensure consistency, right? If the commander was loyal, all loyal lieutenants are going to give the same, are going to, come to the same starting value with which the commander actually started. But if your commander is not honest, then there are going to be things and things and things. And in the end, every of the node is going to come to one consensus decision. So at the end, each lieutenant is going to take a vote across all the values they have received from the fellow nodes along with the commander ones. And this is going to guarantee in a way that loyal soldiers stay in sync even if a few liars are trying to confuse them. Your oral message algorithm is recursive with OM0 being the base case, right? So what we're doing is we're just relaying and rechecking the values through multiple rounds. So yeah, M stands for the traitor. So the more traitors we want to tolerate, the deeper we should or we have to recurse. There's no there's no exception to that, right? So let's just go to the example of the bad lieutenant. Now we have a commander C with Lieutenant 1, Lieutenant 2, and Lieutenant 3, where Lieutenant 3 is your faulty node. So what happens in round 1, commander gives everybody in a one-on-one basis the command to attack, right? Everybody gets the command to attack. Then happens round one. Round one is where every individual lieutenant acts as the commander and gives the command that it received from the commander, or it thinks, or whatever the command it has to give. Given the case of L3, it won't obviously give you attack command, it will give you the command to retreat because it's a faulty node, it's a dishonest node. So all the honest nodes will relay the same command that they got from the commander, while all the dishonest nodes, they're going to manipulate the command. So L1 is going to receive what? Attack from commander, attack from L2, and retreat from L3. So what's its majority? Attack. L2. L2 is going to receive attack from L1, attack from commander it received, and retreat from L3. What is going to take? Attack as the majority decision. So now you know why I took n as 4, because m is 1 and it has to be 3n plus 1, 3n plus 1, 3m plus 1, m1, 3 plus 1, 4. 4 nodes at least in the network. Then let's say we have a bad commander. Commander gives attack command to L1, retreat to L2, attack to L3, and then everybody goes into the round 1 where everybody acts individually as the commander and gives out the commands that they receive from commander in case of honest nodes, and manipulate the command that they received from the commander. But here, since your commander is only faulty and your nodes are honest, so all the honest nodes are going to give the same command as they received from the commander. So L1 receives attack from commander, retreat from your L2, and attack from L3. So it's going to take the decision as attack. L2 receives retreat from commander, attack from L1, and attack from L3. So it's going to attack. L3 attack. So in the previous example where we had a bad lieutenant and the right commander, we studied two conditions, right? Now remember IC2. IC2 standard for validity. If my commander is right, my all honest nodes have to be on the same page as the commander in the last step. And that's it. Since the commander gave the step to attack, all my honest nodes have to be on the attack phase. And when the commander was bad, then comes IC1, that was agreement. All the honest nodes have to be in agreement. So all the honest nodes right now, they take the decision as attack. And every of the honest nodes is on the same page saying attack, irrespective of the commander, irrespective of the bad commander who commanded some of the nodes to go with attack and some of the nodes to stay in retreat. Let's take another example, bigger example, bad lieutenant. Commander gives attack command to all its nodes. Since the commander is honest, then everybody checks on majority, goes in forward, all the loyal lieutenants attack. Then come to the next bigger example, bad commander and the bad lieutenant. You need to go a step down onto this and then just come with one single decision for every node, right? You cannot just stop at OM of 1 here. You have to go to OM of T, OM of 2, until every of the node, it comes to the same majority decision, because when the commander is bad, all your honest nodes have to be in agreement. All your honest nodes have to take up one decision. With this, I think I'm good with it. So if you have any doubts, if you have any concerns, just post them in the comment section. You can also use G-forms if you want me to re-clarify on any videos or re-clarify on any concepts, or you think I've missed some concepts that could have been taken before. Yeah. And if you could extract well from the video, if you found the video helpful for you, just go in, like the video, and subscribe the channel. Thank you so much. Bye bye.